Welcome to this explainer. Today we're decoding one of the most important protocols on the internet. A protocol you use every single day, whether you're on a Zoom call, joining Google Meet, or streaming on Twitch. We're talking about WebRTC, and here's what makes WebRTC genuinely fascinating. It is, quite literally, the reason video calls work at all in a browser. Without it, every real-time communication app would require plugins, native software, or Flash, which is exactly how things worked before 2011. WebRTC changed everything. Section 1. The problem. Why real-time communication is hard. Let's start with a fundamental question. Why is real-time communication so difficult on the internet? The internet was not built for real-time communication. It was built for documents. HTTP follows a simple request-response model. You ask for a page. The server sends it. Done. That works beautifully for websites. It falls apart completely for video calls. Here's the core problem. When you're on a video call, you need continuous, bidirectional data with latency measured in milliseconds. If a packet arrives 200 milliseconds late, the conversation feels robotic. At 500 milliseconds, it breaks. You literally cannot have a natural conversation with half-second delays. Now add 3 more problems. Problem 1. Browsers are sandboxed. They cannot directly access your camera or microphone without explicit permission. Problem 2. Networks are hostile. Firewalls and NATs sit between you and the other person, blocking direct connections. Problem 3. The internet has no built-in security for peer-to-peer communication. Anyone could intercept your stream. WebRTC solves all of these problems simultaneously, and that is what we're going to decode today. Section by section. Section 2. Signaling. How peers find each other. Before 2 browsers can exchange video, they need to find each other. This process is called signaling, and it's the first major piece of the WebRTC puzzle. Here's the crucial thing about signaling that most engineers get wrong. WebRTC does not define a signaling protocol. It's intentionally left unspecified. You can use WebSockets, SIP, XMPP, or even carrier pigeons. WebRTC does not care. You choose the transport, but the signaling messages themselves are standardized. They use SDP, Session Description Protocol. An SDP message is a text block describing everything about the media session. What codecs are supported, what IP addresses are available, what kind of audio and video is being sent. The flow works like this. Client A creates an SDP offer describing what media it wants to send. This offer travels through your signaling server to Client B. Client B reviews the offer. Creates an SDP answer and sends it back. Both sides now know what media formats they can use together. But here's the catch. Exchanging SDP messages does not establish a connection. All you've done is agree on media formats. The actual connection has not been created yet. And that's where Section 3 comes in. Section 3. Network Traversal. The impossible problem of NATs and firewalls. This is, in my opinion, the most brilliant part of WebRTC, network traversal. Most devices on the internet are behind NATs, network address translators. Your laptop has a private IP like 192.168.115. That address means nothing to the outside world. Your router translates it to a public IP when you browse websites. That's NAT. But here's the problem. If you're behind a NAT, another device on a different network cannot initiate a connection to you. Your NAT simply drops the incoming packet because it doesn't know which internal device to forward it to. And let that sink in. Without a solution, 2 browsers on different home networks literally cannot talk to each other directly. The internet's architecture actively prevents it. WebRTC's solution is a framework called ICE, Interactive Connectivity Establishment. ICE tries every possible way to establish a connection and picks the best one. First, it tries host candidates, your device's own IP addresses. If both devices are on the same local network, this just works. Across the internet, host candidates almost always fail. Second, a STUN server. STUN stands for Session Traversal Utilities. For NAT, your device sends a request to the STUN server. The server responds with the public IP and port it saw. This is called a server reflexive candidate. But STUN doesn't always work. Symmetric NATs, common in corporate networks, assign a different external port for each destination. The address the stun server sees won't work for a different peer. When stun fails, IC falls back to its third option, a turn server. Turn stands for traversal, using relays around NAT. All your media traffic flows through the turn server. It's expensive and adds latency, but it works when nothing else does. It's the safety net. ICE gathers all these candidates, prioritizes them, and runs connectivity checks to find the fastest working pair. The result is a direct peer-to-peer connection that survives firewalls, NATs, and hostile network conditions. Let that sink in. ICE, stun, and turn together solve a problem the architects of the internet never anticipated. Section 4. Security and Media. DTLS-SRTP and Media Encryption. This is where WebRTC truly shines. In the early days of VoIP, media streams traveled unencrypted. Anyone with network access could eavesdrop. WebRTC takes the exact opposite approach. Encryption is mandatory, not optional. Mandatory. WebRTC uses two encryption layers. For media, your audio and video, it uses SRTP, the Secure Real-Time Transport Protocol. SRTP encrypts every media packet with AES. Even if someone intercepts your packets, they can't decode your video or hear your audio. But how do the peers agree on encryption keys? That's where DTLS comes in. Datagram Transport Layer Security. DTLS is essentially TLS, the same protocol that secures HTTPS, but adapted for UDP. The unreliable datagram protocol that real-time media uses. The DTLS handshake runs over the same peer-to-peer connection established by IC. Peers authenticate using certificate fingerprints exchanged during signaling. Once DTLS completes, it derives the SRTP encryption keys. From that point forward, every media packet is encrypted end-to-end. And this is critical. The signaling server never sees the media. It never possesses the encryption keys. Even if your signaling server is compromised, the media remains secure. This is cryptographic enforcement of privacy. WebRTC browsers will not even allow unencrypted media channels. You literally cannot disable encryption. Now, bandwidth adaptation. Network conditions change constantly. Your Wi-Fi dips. Mobile data fluctuates. WebRTC continuously monitors conditions using REMB, Receiver Estimated Maximum Bit Rate, and GCC, Google Congestion Control. When bandwidth drops, WebRTC automatically reduces video quality or switches resolution to keep the call running. You have experienced this. Your Zoom call gets blurry for a few seconds, then clears up. That's WebRTC bandwidth adaptation in action. Section 5. Architecture, peer connections, and beyond. So far, we've focused on one-to-one calls, but WebRTC scales far beyond that. For small groups, you can use a mesh topology. Every peer connects directly to every other peer. But mesh falls apart beyond about 6 participants, because upload bandwidth grows with every new person. For larger groups, 2 server-side models dominate. First, SFU, Selective Forwarding Unit. Each participant uploads once to the SFU. The SFU forwards streams to everyone else without decoding. It's a router, not a transcoder. This is what Zoom and Google Meet use. It scales beautifully. Second, MCU, Multi-Point Control Unit. The MCU receives all streams, decodes them, mixes them into a single composite grid, re-encodes, and sends one stream to each participant. Computationally expensive for the server, but efficient for the client. SFUs have largely replaced MCUs now, and there's one more thing most developers overlook. The data channel. Beyond audio and video, WebRTC supports arbitrary peer-to-peer data transfer. Low latency, direct, with no server in between. This enables file sharing in calls, multiplayer game state sync, and even fully decentralized applications. Let that sink in. WebRTC isn't just a video protocol. It's a general-purpose peer-to-peer communication framework. WebRTC brings together signaling, ICE, stun, turn, DTLS, SRTP, codec negotiation, bandwidth adaptation, and data channels into a single coherent standard available in every modern browser. No plugins, no downloads, no flash. It solved the hardest problems in real-time communication so elegantly that developers can add video calling to their applications with a few dozen lines of JavaScript. Thanks so much for joining me today on this explainer. If you want to see more deep dives into the protocols that power the internet, subscribe and hit that notification bell. Keep building, and I'll catch you next time.